Hello everyone, I'm Cornel Douglas and this is my math regression project for Mr. Porter's Calc 151 class. What my project is about, I'm an EET major and my project is about the energy uses of coal over the course of 160 years. The reason I used coal instead of energy efficiency was because I couldn't find anything dealing with energy efficiency that gave me data with exact points. Most of it was just me estimating the points and I didn't feel right using it. And I ended up finding data with coal with exact points, so I just ended up using that instead. But when I got closer to the end, I did manage to find energy efficient data that had exact points, way more than 9 points that I could have used. But I didn't want to use that and redo everything all over again. This is my data. As you can see, X is our years after 1850, and Y is our coal used in quadrillions. Our rate of change is 8.9 year per coal used. My regressions are cubic. My cubic regression and my quartic regression. The graph going right through my data is my cubic. The squiggly one is my quartic graph. My cubic graph gave me a better looking graph than my quartic. My quartic gave me an upward concave graph, while my cubic just went right through everything. Well, not right through everything, but like if you zoom out, it looks a lot better. My regression split. On the left side, it's my cubic. On the right side is my quartic. That little break that you see in between the graph, that's x equals 80. That's where my graphs broke at. To make them continuous again, I would have to calculate the difference between the two graphs. Then I raised the left side by that difference, which was 1.048, to make my graph continuous again. The concavity of my cubic graph, x is our years, y is our second derivative, which is what we use to find our concavity and where our graph is increasing or decreasing. For y, 0 was a negative value and everything after that was a positive value. My concavity for negative numbers was down, while my concavity for positive numbers was up. So all negative values are down, concave down, all positive values are concave up. All negative values are also constantly decreasing, while all positive values are constantly increasing. And to prove this, I'm going to use my virtual TI-83. I'm going to turn it on. Then we're going to zoom out. And as you can see, it matches my data perfectly. The endpoint of my cubic graph is increasing infinitely, and the other endpoint of my cubic graph is decreasing infinitely. Another thing you might notice about my graph is that I don't have any absolute maxes or mins. I only have local maxes or mins, which is my negative infinity and my positive infinity. But even though I don't have any absolute maxes or mins, what I do have is an inflection point. And to find that inflection point, we're going to use my second derivative. And to find our second derivative, you're going to do this. You're going to do n deriv y1 comma x in y2, which gives you our first derivative. And to get our second derivative, you're pretty much going to do the same thing, but instead of using y1, you're going to use y2, which gives us our second derivative. Then we're just going to go up, turn that graph back on, and we're going to go on our graph. Wait for it to load up. You won't notice my second derivative because it's really, really small. Still loading, still loading, still loading. Now we're going to do second, calculate, intersect, enter, enter, enter. By doing this, where my original graph and my y-intersect meet is where my inflection point is. Every value after that point is increasing infinitely. Every value below that point is decreasing infinitely. That's when my graph switches from decreasing to increasing or increasing to decreasing. And that point is 5.137414. Another way to do this is by using Newton's method. To do that, we're going to do second quit, clear that out. We're going to hit 0, stow that as x, hit enter. Every time we put an x, x will be 0. We're going to do x minus vars y1 divided by our second derivative, not our second derivative, our first derivative. Since our first derivative is already in y2, we're just going to do y2 instead of writing everything out again. Then we're going to stow that in x, alpha x. Now you're going to keep hitting enter till your numbers begin to repeat. When your numbers begin to repeat, that is where our graph hits 0, which is also our inflection point. It might be close to our inflection point, I mean. As you can see, after 3 clicks, my graph hit 0, and that is my inflection point right there. It's not exactly as it was using the intersection method, but it's pretty close to it. Next, we're going to find the area under our graph. What we're going to do is second calc 7. We're going to set our lower limit to negative 0.5, our upper limit to 1 to 60.5. Oopsie. 1 to 60.5. Hit enter. The reason why I added and subtracted 0.5 from both sides was so that both sides would include all our data, all of our data, because if we did 0 to 160, we'd end up missing a day. So the best way to do it was just by subtracting 0.5 or adding 0.5 to either side. Then we're going to hit enter, and as you can see, my area under the graph is 1,714.87. To find our rate of change per year, we're going to divide that number by our number of years. And our coal change per year has been 10.71 quadrillions of coal. Our years got canceled out because we divided both by years. Well, not both. Yeah, we divided both by years because this is years per coal used, and we divided by years, and all that left was the coal. My margin of error. For my margin of error, we used my coordinate graph. I guessed ahead 23 years in the future because I didn't want to use a point that was exactly on a graph, so I decided to guess ahead. My y1 is 30.647, while my y2 is 0.72802. X equals 183 years after 1850. To calculate our error, we multiply y2 by plus or minus 0.5 years, and then we divide it by y1, and we get a margin of error of 0.01%, which is less than 1%, which is negligible. So that's pretty close to my data. In conclusion, I find that we need a newer energy source that's more reliable and more renewable. Some have suggested using nuclear energy as a way to solve this problem, but it's not really the answer because it's not reliable enough and it's too dangerous to actually mass produce. Like, for example, if we built more nuclear power plants everywhere, we'd make ourselves vulnerable because it'd be easier for people to attack these plants. And it's also a danger to us because these plants produce a crap ton of waste, which destroys the environment. So nuclear energy isn't really all that reliable.